So the correlation coefficient is a numerical measure of the strength of a linear relationship between, obviously, it's the whole chapter, right? Two variables. So this can range between negative 1.00 and positive 1.00. If it's 0, that means that there's no association between the two. If it's 1, that means we have a situation where everything is pretty much on the line. Correlation coefficient is abbreviated with R. Something like this, right? A scatter shot, like a shotgun, is going to be no correlation. R is equal to 0. So now we know what's going on here, or what a correlation coefficient is, but let's couch it in the example that we were talking about before with the salespeople and their number of things that are sold, right? So if we go back to that example, if I can draw a straight line, we have calls, and then we have sales, and we had different points, something like that. And so as a visual clue, I'm going to put what the average of all the Y values are. So the average of all the sales. The average of all the sales is going to be 45. And remember, whenever we're talking about averages, we put a bar on top of whatever that variable is. So Y bar, the average of just this variation, right? Just the up-down variation. We took all those things and we averaged them, and we got 45. So we only averaged the sales, and the average of all the sales for all these particular salespeople is 45. And then we wanted to figure out what's the average of the sales calls, right? How many sales calls on average did they make? And so we went ahead and just computed the average of just the X's, and we found that the X bar is equal to 96. So on average, each salesperson made 96 sales calls, and on average, they sold 45 things. When we have a data point where the number of sales is less than the average, right? So this data point right here, then this is, a deviation from that average. So this is a negative deviation from the average, right? If it's below the average, and then this is a positive deviation. And so really what we're looking at the end of the day, when we're using our correlation coefficient formula, which I'm going to write over here on the side, and again, we get to use Excel and other kind of things to do this for us, so we're very rarely going to have to actually go through the work of doing this, but it's important for us to understand kind of what's going on behind the scenes, right? So this R is looking at the sum of all of the individual X's, so Xi, all of their deviations from the average, from 96. And we're trying to look at, okay, if this value is above 96 here. Is it also going to be above 45, right? And so we want to know, are both of these things deviating from the mean, from their individual means in the same way, right? So for this particular point right here, right, this part of it would be positive because it's got, you know, x is equal to 100 or something like that, right? So it'd be positive 4. And then for this part here, right, it's above 45. So let's say that this is 75 or something like that, right? So 75 there, 100 there. And so 75 minus 45, this would be 30. Now, the significance, the size of these values don't necessarily matter so much. Well, they do matter because they're going to tell us the strength or the strength of the correlation. But what matters more than the size, even though the size is important, is the sign of them, the direction of them, right? Are they both positive? So for this particular point right here, right, both of these points, for this particular point right here, both of these terms are positive. And then we're going to divide the sum of all of these products, right? These are two things that are multiplied together by a constant at the end of the day. So we're going to do this on the numerator first, and then we're going to divide by the degrees of freedom times the individual standard deviation of x times the individual standard deviation of y. So we don't really need to understand the denominator so much as just to know that that the larger standard deviations are going to cause there to be smaller correlation coefficients, right? So if there's a greater spread, you know, so the standard deviation, right, is essentially telling me how much on average I can expect y values to be deviating from their particular mean, right? In one direction or another. That's the standard deviation. The variance is telling me how wide in both directions, right? The range is also telling me that in a different way. It's telling me the maximum. But a standard deviation is just telling me the spread in the simplest terms possible, right? So if there's greater spreads for each one of your individual data sets, right? If these values increase, then because they're in the denominator, that means your correlation coefficient is going to decrease. But again, the important part is mostly what's going on in this numerator here, right? It's talking about, we look at each one of these points. So we do this calculation for each one of these points, right? So let's just kind of, again, assume away the denominator. And let's just do for this point, and let's do it for this point, and then let's do it for this point, right? And so we have something over here where it's going to be, you know, 100 minus 96 times 75 minus 45, right? That's for this point right here. We already defined that, the 145 here. I guess I could label these a little better. So this one is 100 on the x, 75 on the y. This one up here is going to be 115 on the x and 95 on the y. So anyway, so this is going to be 45 because that's the y bar. So we're going to do this, and then we're going to add 115 minus 96. So the 96 doesn't change and the 45 doesn't change. It's just each new data point is going to give us new values for this yi and this xi. And then the third point, right, which I picked out over here, just so we had some variation, is going to be, well, what if x is to the left of 96, right? So if this point was something like 86 and then 55. So then we're going to add another term as part of the summation, right? And this one is going to be 86 minus 96 times 55 minus 45. So now we're going to get a negative number over here, right? Negative 10 times positive 10. So in a way, this term, right, being negative 100, is taking away from these terms, which are talking about the positive correlation, right? So both of these terms, this is going to be 4 times 30, right? So this is 120. This is going to be 19 times 40, whatever the heck that is, right? Which is a lot. And so this is going to detract from that. So these values over here, and then if there were any values over here, they would be detracting from the correlation coefficient. And the correlation coefficient is going to get larger the more that the yellow dots are lined up on this kind of straight and narrow line, right? So the more that they're lined up on that 45-degree line that's radiating from the two means, the more that we're going to have a higher correlation coefficient.